Okay. I think we're good to start now, so I'll just start. Okay. First off, thank you everyone for joining us here on this Thursday evening. My name is Shazia, and I'm the Vice President of Industry Relations here at UTMS. I will also be the MC for tonight's talk, and I'm going to give a few words on UTMS before I hand it over to Untether AI to continue. UTMS is an academic student organization at U of T, founded in 2017, that stands for University of Toronto Machine Intelligence Student Team. We are a community of machine learning enthusiasts, and our mission is to provide opportunities for students and the public to get involved, ultimately to clear the myths that surrounds machine learning. UTMS pursues many initiatives throughout the school year. We have multiple talk series, such as our academic talks, where we invite distinguished researchers to share the latest breakthroughs and applications related to machine learning. We also have a machine intelligence workshop series led by our own team, called MISS 101. This is a chance for beginners or those who want to quickly brush up their skills. They are released bi-weekly on YouTube, and you can learn the skills at your own rate. We even have mentors on YouTube and Discord who are always here to help. It is free for everyone to access, and it is great preparation to join our project teams, which I will talk about next. So our project teams work on a variety of interesting applications, such as out-of-distribution detection, hand gestures to control web browsing, and mastering the popular game of Cards Against Humanity. You can learn more about our projects on our website. In the chat, I believe we shared the presentation slides, which contain all the links you see here, including contact and our social media. Additionally, we have an active community on Discord and bi-weekly bite-sized machine learning newsletter, which covers everything from industry to research, careers, and even our own events and projects. Today, we are starting a new talk series called Entrepreneurship in AI, where we invite founders to share their technologies and startup journeys. Our second talk is coming up in the middle of February by another startup called Corbett AI, where you will learn about how they're leveraging AI to revolutionize online education. They will additionally demo their learning platform and deliver a tutorial on data processing. This is a great chance for anyone interested in entrepreneurship or want to prepare for our upcoming hackathon happening in late February. Our third talk will be delivered featuring SyncReview. And this is SyncReview is one of the most highly regarded media agencies for emerging tech, who performs an in-depth analysis of trends and outlook for AI industries. If anyone is interested in supporting UTMS and continuing to provide initiatives to students and the public, such as delivering a keynote or supporting our projects with donation, or even providing us with monetary value or offering mentorship, please send us an email and we would love to chat with you. Today, we will hear from 3 speakers from Untether AI. First up, we have Paul Grouchy, who is going to speak about quantization of neural networks, followed by Dr. Martin Snelgrove, who will discuss the mathematics and physics behind neural networks. And finally, Darrick, who will share the story of Untether AI as a startup. Without further ado, please welcome Paul. So you can start to share your screen now.
All right, is that coming through?
Yeah.
Great.
Yes.
Well,
it's all
awesome.
good.
Thank you very much for that warm introduction, and thank you very much for the correct pronunciation of my last name. It is not often that that goes well the first time around. So it is in fact Grouchy or Grouchy, despite its spelling Grouchy. I have a background in aerospace engineering. My PhD was at UTIAS, which is the University of Toronto Institute for Aerospace Studies, where I studied machine learning for robotics, space robotics applications. So I was looking at sort of multi-agent autonomous systems. Professor was Professor Ontario, who you have had in the past, or maybe even currently have in your curriculum. And so currently, I'm the team lead for the neural network team at Untether AI. And the sort of the main thing that our team looks at is trying to come up with what we call U-friendly versions of neural nets. So by U-friendly, it's kind of an internal term we use for untether aware, sort of hardware aware networks. And I'll get more into what that means later in the presentation. And on top of that, we sort of are building this high-level framework to allow our users to automatically translate their networks into something that is ready to be run on our hardware. And sorry, I meant to mention, in terms of questions, I think maybe I'll take a brief pause in between my presentation and the next one to take any questions, but there'll also be a Q&A session at the end for all three of us. Oops. Right, okay. And so the major challenge that we're dealing with is when you convert these models, there's a potential to lose accuracy, and I'll get into that a little more later on. And so a lot of our work is actually trying to figure out how do we preserve accuracy when we translate these models for our hardware, and how do we gain back lost accuracy through specialized training techniques. Okay, so I was told that the audience would be quite mixed, and so I'm going to start from machine learning 101 and work my way all the way up to quantization. So we'll start at the basics. I apologize if you know this stuff already, but it's good that we're all to be on the same page. So at a very high level, machine learning can be broken up into two pieces. You've got your training phase and then your inference phase. So the training phase, it comes in a lot of different forms, but a common one is through supervised learning. So supervised meaning that you have data and you have labels for your data, which is where the supervision comes from. So a common example is sort of image classification. You have a picture of a dog. You want to know, is this a dog or is it a cat or is it a boat or whatever? And so your labels, then you'll have images of dogs, you'll have images of cats, and you'll know someone will have gone and annotated each image as this is a picture of a dog, this is a picture of a cat, so on and so forth. And you push this data through one of myriad training algorithms, and the end result is a trained model of some sort. Now that you have this model, you can take it out into the world and start your business and make your millions. So the basic idea here is that you have new data coming in. This is unlabeled data. This is data the model has never seen before. And if you trained your model correctly, it's going to be making accurate predictions about whether or not, for example, this is a dog, this is a cat, so on and so forth. And this is where Untether AI is focusing. We're focusing on inference, specifically inference acceleration. So once you have a trained model, the idea is you would come to Untether AI and use our hardware to be able to accelerate your inference. So the machine learning is a very broad field. Neural networks are one of the more popular aspects of machine learning, but there's actually quite a variety of different types of models out there. So I'll talk a little bit about what a neural network model might look like. So this is again one of that model block in those previous diagrams. So this is a simple feed-forward neural network. It's fully connected, which means every node is connected to every subsequent node, sort of passing through the network from input to output. Over here on the top right, this is the equation that just figure this out, and then you'll understand deep learning. Basically, it's more or less just a matrix multiply. You have your weights and then your activations, which are the signals that are flowing through your network. And then this is a nonlinearity that I'll talk about in a second. So in this network, you can think of the input nodes, if you're thinking about images, as pixels. So these are the pixel values coming in from the image. And then these connections between nodes are weights. So these are trainable parameters. And these are what are updated during the training phase of the network. So the inputs come in, these are pixels. They get multiplied by the weights and then go to your hidden nodes here. They go through the nonlinearity, which I'll talk about in a second. And then again, they get multiplied by the next set of weights and then become an output. And the output could be something in the case of classification, where you take the maximum of your outputs. You have maybe 10 classes. You take the maximum of your outputs, you figure out what class that's aligned with, and that's the prediction of the model. So if dogs are class 0, then if the maximum output is the first output, then you've correctly predicted a dog, or incorrectly if it's a picture of a cat. So coming back to the weights, this network has 42 weights, so 42 learnable parameters, and these are in floating point 32. So 32-bit floating point, typically, not always, but typically. The activation function is what gives you some nonlinearity. So this is where the kind of nonlinearity in the networks comes from. A typical one is ReLU. So the idea here is that if the result of this operation here is negative, then you set the output, the activation output, to 0. Otherwise, you pass it through unmodified. Yeah, and so that's deep learning. Go forth and predict. So I'll talk a little bit about a real world example, because predicting pictures of dogs and cats actually isn't that useful in the real world. Here's a good example of why. Here's a picture with a dog and a cat, and if the network is only predicting a single class, it's not going to really be all that useful for this sort of image. So this is where object detection comes in. So object detection uses these image classification networks as a backbone, and it adds on a few extra layers, which are used to then predict what objects are in the scene, and also it helps localize them. So it'll actually draw a bounding box around where in the scene those objects are. So an object detection algorithm can predict both a cat and a dog in the same image, although I'm not sure if it would get this right as being a dog, because it looks kind of funny. And one application of this is self-driving cars. And so this is obviously a very hot topic in machine learning. Lots of work has been done on it. There's still a lot more to go. And a couple of interesting properties about this task is that these networks have to run quickly. If it's detecting where these cars are on the road, and it takes three seconds to make a prediction, if a car swerves into your lane, it's already way too late by the time you realize that the car is moved in front of you. So these applications require really low latency, so on the order of 5-10 milliseconds, to get really quick reaction times out of the networks. And also, you can think that a self-driving car won't just have one object detection network running. It might have multiple cameras, which will require multiple networks running to process it. Might also have a LiDAR, giving you maybe point clouds, so different type of processing. And then maybe a high-level decision-making algorithm of some sort. So you're going to have a whole lot of different algorithms deployed on a single vehicle. Okay, so now that we are all up to speed on deep learning, I will talk a little bit about quantization. So as I mentioned earlier, the weights are typically in 32-bit floating point. And our hardware, one of the ways we do sort of acceleration is we actually use integer math, specifically int8, so 8-bit precision. So obviously, you can't just cast a 32-bit float down to an int and call it a day, because typically weights are between, let's say, -1 and 1. So if you just do a cast, you're only going to get 3 values: -1, 0, and 1. But really, what you want to do is you want to represent your full range of weights or activations using those 8-bit ints. So the way we do this is through what's called linear quantization. So the idea here is you find the min and the max, let's say, of your weights, and you scale that to fit within the 8-bit range. There's two ways of doing this. There's symmetric quantization and asymmetric quantization. So symmetric quantization means that you are scaling the values and they're centered around 0. So you look at the absolute value of the maximum of the absolute value of, let's say, your weights, and you make the minimum to be sort of the negative version of that absolute value, and the maximum to be the positive version of that absolute value of the max. And this works well for values that are centered around 0. But if you're looking at sort of an activation coming out of a ReLU, 0 is the minimum, and then let's say 5 is the maximum. So if you scale between -5 and 5, you're actually wasting a whole bunch of bits that you're never going to use to represent your values, your floating point values. So this is where asymmetric quantization comes in. So asymmetric quantization lets you actually move the center point away from 0, and then have different values for the min and the max. The trade-off there is computational complexity, and I will talk about that in the next slide. The general rule for these sorts of presentations is don't do math, but I feel like a bit of math here is worthwhile, just to kind of get a sense of what's actually going on under the hood, because it's not, as I said previously, it's not so simple as just taking a cast, doing the math, and then casting back to float in the end. So this is an example where we try and do the matrix multiply that we saw previously, but using quantized values. So here we have R, which is our real value in float point 32, and then we can represent that using this equation here. So we have S, which is a float scale. We have Q, which is our int8 quantized value, and we have Z, which is our 0 point, which is what lets us, in the asymmetric case, move where 0 is in the range. And so if we say that R1 is the weights, and then R2 is the activations, and then R3 is the resulting floating point value from the matrix multiply, you can sub this equation in and you get this equation here. And one thing to note is that there's 3 different scales, S1, S2, S3, and 3 different 0 points, Z1, Z2, and Z3. And this is because we're quantizing everything differently. So we're going to use one quantization scheme for the weights, a different one for the activations, and then a different one for the outputs. If you use the same one for everything, you're going to end up not getting the right, capturing the right precisions, and you kind of lose a lot of accuracy that way. And so you can move things around, recombine here, there, and everywhere, and eventually what you get is this equation here. And the nice thing is that all of a sudden we've returned to a matrix multiply, and this is a matrix multiply of the ints. So let's say this is the integer quantization values for the weights, Q1, and then Q2 are the activations, and then Q3 are the quantized outputs of the operation. So coming back to the conversation about symmetric versus asymmetric, there's some key things to notice in the bookkeeping that has to happen to actually be able to return from quantization, be able to actually, using this equation here, get the float value back from the quantized result. And this term here is a constant. You know the number, n, the sort of number, the values, the number of weights, let's say. These are your 0 points, you know those ahead of time, not a big deal. The challenging one is A2. So A2 is the sum of all your activations. So this is like the signal moving through the network. The problem here is you don't know this ahead of time. You only know it at the time you get to this layer, because this might be an image you've never seen before. Here it comes. You've actually got to calculate then the sum of all of the activations at this layer. So that's a significant compute cost that wasn't there in the floating point approach. But the neat thing is it's multiplied by the 0 point of the weights. So if you quantize the weights symmetrically, the 0 point of the weights is 0, and then you don't have to worry about this term. And the rest of the terms can all be calculated ahead of time. You can fuse them together in a single operation, and you just have one additional add. So this is what I was talking about earlier about the trade-offs between symmetric and asymmetric. Asymmetric has better representation, but symmetric gives you significant compute benefits. Oops. Okay, and my last slide is about retraining. So even though you've spent all this time figuring out the quantization math and you are really excited, you've got it all working perfectly, it does a great job of representing the floats. These are big networks. Sometimes they can be quite sensitive, especially really compressed networks like a mobile net or something like that. So even you've put all this effort in, you still might not get the accuracy that you're looking for compared to the floating point model. And not to worry, there are actually techniques out there to kind of gain that back. So the main one I'll talk about is called quantization aware training. The basic idea here is you can continue to train the floating point model. So you continue to use floating point weights and activations, but you inject noise in each layer that simulates the noise that you will see when you do quantization. So that's sort of illustrated in this here. So on the left, you have sort of integer inference. So you have integer weights, integer inputs, you go through a layer, it accumulates into int32, and then you scale that back down to int8 and through the nonlinearity, and then you keep going in int. You train again, and this is in float 32, but you have these additional noises, these additional nodes, which inject the noise from weight quantization, and here the noise from the activation quantization. And so this actually lets the network adapt to the eventual noise it will see when it actually gets quantized. And then when you go ahead and actually quantize this network after a little more retraining, all of a sudden you'll see your accuracy is doing much better than beforehand when the network had never kind of learned to adapt to that sort of thing. And so that is a run through from 0 to int8 models running in accelerated inference. I can take a few questions now before we continue on.
Or if not, we can roll. Paul, we might as well leave your screen now. I'll just ask you to advance. Otherwise, we've got the usual Zoom fuss of getting the next guy's screen up.
Works for me.
Okay, so I'll start talking about chips. So Paul's talking about the math of it in kind of an abstract world. I'm responsible for helping turn that into silicon. So just from my background, I taught at Toronto 82 to 92, so I taught some of your profs. I'm the chief technology officer and one out of the three founders of Untether. There's another one going to come up and talk to you shortly. And I've been in this technology for 30 years. So there's early versions of the kind of architecture we're looking at were starting to show up in the 1980s, 1990s. There were old machines called thinking machines, which were talking about AI, but back in prehistory. And so we were involved in some of that. And my technologies are signals and silicon. I'm used to thinking about how you represent things, big vectors and things, and how you turn that into a physical system. Moving on to the next gadget. So here I stole Paul's slide because, why make my own? And then I scribbled all over it. And what this is about is saying, well, Paul's telling you got to do these calculations, but they've got to be physically done somewhere. Oop, excuse me a second. Sorry, just someone ringing the doorbell. So he's showing these numbers, and then the lines have multipliers on them, and the green blobs are places you put things. Where physically are those things going to be? Are the numbers on the black lines going to be placed next to the blue dots or to the green dots, or are they somewhere in between? And what are those numbers? What is the representation of that? Paul told you about int 8, which is where we are right now. Hey, Sherry. Sorry, it's the joys of working from home. So then with these activation functions Paul was talking about, how are we going to implement those? One of the problems you're going to have here is that people keep writing papers. There are 100 papers a day being cranked into archive.org, and we're developing a chip. It costs millions of dollars to develop it, and it takes around a year to do it. So by the time we get our chip out on the road, there have been 50, 100,000 papers written, some of which have activation functions in them that nobody was warned us were going to happen. So how are we going to do that? Right? How are we going to predict the future of activation functions? Now, one clue on the first question, which is where do you put the coefficients? The coefficients are these WJKs. And the exciting thing is you'll notice that the letter K appears twice in that formula. So it looks like maybe the WJK should go with the AK. But the other thing that appears twice is J. So AJ has got the WJs in it. So maybe the W should be with the A's, with the outputs. Do they belong with the outputs or the inputs? Well, you're going to have to move somebody. And Paul gave you the hint that the outputs end up as int 32s. The inputs are int 8s. 32 is a bigger number than 8. If I'm going to move something, it's not going to be 32s, it's going to be 8s. And I'll talk to you in a minute about why I care about moving. Next slide, Paul. Now, Paul also showed the picture in the bottom with the red hot data coming in and getting cooler as it goes through the computation. That's not how it works. You put in data, it's nice and cool, and then computers run red hot. So this is an infrared picture of a data center. This is what matters on the right is heat. And why do I say it matters? Well, right now, about 1% of the electricity in the world is being used for AI, which is a ridiculously large amount because there's a lot of electricity in the world. But it's worse. AI at the moment has a 37% cumulative annual growth rate, meaning essentially that number is going to double every 2 years. So by the end of the decade, 15-16% of the world's energy consumption will be AI. Well, this is nuts, right? This is not going to happen. The only way that happens is if people start reopening coal-fired generating stations and kill us all. And so let's not let's not do that. So what can you do to get the heat down? So heat's not some minor secondary thing. Computation produces heat. AI does computation. This is the big problem. And so this is what Untether is about. We've got our current machines are around 8x more efficient than NVIDIA's best machine. So that means you can double 3 times. So we've got a 6-year head start on destroying the Earth. We'll stop it for 6 years. Our next chip, we hope, will push it back for another 5 or 6 years. We hope every couple of years to help just push the doom due to AI power consumption back a little bit. And maybe at some point people will stop inventing algorithms that blow up computers. Okay, so heat. It's a serious problem. Heat is not green. Next slide. So here's the physics of where heat comes from. I thought I'd go for a nice hokey picture. This thing is a simplification of how a computer works. You've got an input from somewhere. It runs through a wire and it hits a transistor. And the transistor then makes more electricity go through another wire and so on. So just do this 10 to 100 billion times and you've got a chip. So what's the energy on this thing? Well, the physical mechanism that makes the transistor able to switch things around and make the next gate do something interesting is that unlike charges attract, that if you suck electrons out of a gate, you get a positive charge there, and that attracts electrons in the silicon underneath, and then that forms a channel, and off things go to do the next thing. So we're using this capacitance to make the thing work. But unfortunately, the length of wire that goes to that transistor kind of works the same way. So if you're going to suck electrons out of the transistor, you're going to be sucking them out of that piece of wire on the way too. And so you're going to get some charges attracted in the silicon underneath the wire. And that's an unnatural state. Those electrons don't really want to be there except for the shortage of electrons you put in the wire. And an unnatural state consumes energy. You have to spend energy to get yourself to this state. Now, it turns out, if you go back to the Middle Ages, like the 1980s, when this technology was originally getting developed, 1970s and 80s, transistors were big and heavy, and wires were short and light. And people, when they were thinking about how hard computing was to do, thought, well, the transistors are doing the interesting work, and that's where all the energy is, so you could focus on the transistor. This has not been true for the entire 21st century. These days, all of the energy is going into the length of wire to get to the transistor and not into the transistor itself. And why is that? Well, they taught you in first year physics that when you scale things, something that's linear, so if you divide every length by 2, then the length of wire goes down by a factor of 2. That's good. You've got half as much energy there. And the area of the transistor goes down by 4. So you've got 1/4 as much there. So every time we get technologies better with finer lines, yeah, there's less energy consumed, but more of it is due to the wires and less due to the transistors. To the point where for the last 20 years or so, if you want a first order estimate of how much power you're burning, just look at how much wire you've got. That's what's hurting. So our life is about not transmitting data where you don't have to. And there's some numbers there. You can say a millimeter of wire costs you around 300 femtofarads. So it's going to cost you these days a couple of hundred femtojoules, which doesn't sound like a lot, 200 times 10 to the minus 15th joules to get a bit to travel a millimeter. But remember, we clock at a gigahertz, so your 10 to the minus 15th happens 10 to the 9th times a second. And we don't have 1 micron of wire or 1 millimeter of wire. We have a chip that's covered in wires, spaced nanometers apart. And so a typical chip these days has kilometers of wire on it. So the 10 to the minus 15th started to sound pretty small, but you multiply it by 10 to the 9th hertz and multiply it by 10 to the 9th millimeters, and you're getting into the kilowatt range, which is where chips all are these days. So there's our problem. You shouldn't be hauling data all over the place. So moving to the next slide. So here's an extremely stupid way to do computing. This is called a CPU. All right, so in anybody's Xeon or whatever, when it does a fetch, it does it the way von Neumann said you should do it in 1947, which is that you send an address to a chip somewhere on the far side of the Earth, maybe 2 centimeters away, and it goes and rustles around inside a square centimeter of silicon and finds your bits and then shoves them on a piece of wire and sends them to you. So just to get some bits to do a computation, you've sent the data tens of millimeters, like unbelievable distances. So this is stupid. Nobody would ever do computing like this, except everybody who does computing. And this is why 1% of the world's energy is busy just shoveling data back and forth into this chip. So this is insanely wrong. It's also what people do. Next slide. This is another really, really wrong thing to do. This is what Cerebras does for fun. They do one giant chip. So they're not taking the data on and off chip, so they think they're being good. But that chip is still tens of millimeters across. So you're still sending data tens of millimeters to get from one spot to another. These guys, that chip burns 15 kilowatts. The element on your stove that's boiling water burns 600 watts, right? You could heat the water for your house continuously, taking showers, offering showers to all your friends, just for cooling this chip. So these guys are not going to save the Earth from AI workloads. So one thing is, they're making the mistake of trying to do things in 2 dimensions where you should be in 3 dimensions. If I've got a bunch of things to connect together, I'm much better to hook them together in 3D than in 2D because I can get them closer. So you should take that big chip, chop it up into little ones, stack them on cards next to each other, and wire them together in 3D. So that's a terrible mistake they've made. But they've made a couple more mistakes too. The way I showed you for transmitting information from one spot to another is how you do it on chip and how those guys do it. When you look at wires, though, they have capacitances, which is what I showed on the previous diagram, but they have inductance too. And so in the late 19th century, people discovered that actually you could get the inductance to cancel out the capacitance and you didn't have to spend any energy to send data on a wire. Well, it's not quite true, but you can certainly spend a lot less than if you don't cancel out the capacitance. So when people are trying to send data a few centimeters, nobody does it with wiring on a chip anymore. They convert it to a transmission line form and send it by a distance-free or roughly distance-free method. And so they get better efficiency. Now, you don't do that on short distances because converting it to transmission line form is a pain in the ass. It's a lot of transistors and power to do that. But if you have to go serious distance, that's what you should do. And in fact, going to the memory chip on an off-chip device, that's with the transmission line these days. And if you're going to go for meters of distance, if you're going to go to the other side of a data center or across the Atlantic, then even better is you convert to optical form, which is really good quality transmission lines, basically. So the pictures on the bottom say, look, when you're moving your haul of wood a short distance, you use a wheelbarrow. That's what you use on chip. It's nice and simple, and you can take small quantities, small distances. When you're going a little further, you load it onto a train. That's the transmission line. And when you've got to go a long distance, like a meter or two, then you put it on long haul shipping and get serious quantities of data pumping around. So that's optical Ethernet on the right. That's wiring on the left. Okay, so this is also a bad idea. What have we got on the next chip? Okay, so this is the Google's TPU3. So this is Google's tensor processing unit specialized for doing AI. And the picture on the right is the thing physically, and what you can see there is that it's water cooled. That's a bad sign, right? If they have to pump liquids over it to stop the chip boiling itself, then it's probably not going minimal power. Why is that? Well, look at the chip picture on the left. Oh, actually, sorry, that's, I don't know how that happened. There's sorry, that top slide should, I don't know if you can nuke the Xeon that's on the top there, but the thing on the top left is the TPU V3, and you can see it's got a
presenting and start again. I've moved it.
Oh yeah, okay, right. So the picture on the left in the blues and golds is what the TPU does. It's got a giant matrix multiplier that's only good at one size of matrix multiply. And when it's done with the matrix multiply and it wants to do ReLU, it ships the data all the way off to the corner of the chip to a gadget that's specialized at doing ReLU. It can't do GeLU. It might be able to do sigmoid, and it certainly won't be able to do some new nonlinearity that somebody invents next week. But so A, it can't do what you want, and B, you have to go 10, 15 millimeters to the other side of the chip to get the job done. And that's why this thing's water cooled. Right? So that's also wrong. Okay, now the slide we're not showing you, because you have to sign an NDA and come and work for us to find out is the right way to do it. But because we know how a matrix works, like we know that you keep the coefficient next to the output, and the distance bits travel for us is around 50 is around 50 microns. Right? Now we're trying to get it down. We've got one volunteer for the NDA, so yeah, I'll get Darrick to work on that. But when you look at our chip, it just looks like one big blob of memories with tiny little processing elements stuck next to them, and then software figuring out in advance where the data has to be, because you don't want to move it around on the chip. And when we do sigmoids and things, we understand the Weierstrass theorem. We understand that you can build anything with a polynomial. We know that segmented polynomials are even better. We've even got people trying to remember how the Newton-Raphson method works. So Paul's got lots of vicious numerical math he has to do. But moving to the next slide. So I've spent a lot of time talking about not moving data. That's our big pleasure. The other thing is to talk about the int8 and floating points and so on that Paul was talking about. So FP32 sounds like it's maybe 4 times as big as int8, but it's not. It's much, much bigger than int8. First of all, when you multiply numbers together, if you remember grade school, how you multiply, you end up doing an n squared process, right? You've got n bits times n bits. You end up with more or less n squared operations to get the job done. So a 16-bit int is 4 times as much work as an 8-bit int for a start. That's why we really like small numbers of bits. And secondly, floating point is a pain. So the thing at the bottom left is showing why we hate floating point. So that's one tiny little piece of how a floating point unit works. And in floating point, you get an exponent times, you've got a number times 2 to the some exponent. You multiply them together, so you add the exponents and multiply the numbers. That sounds easy. Then you add things together, and now this is horrible, because I'm adding 2 things that are shifted by different amounts, and I have to figure out which one shifted more, and then shift the other one over to line up, and then do the addition. And unfortunately, it did a cancellation, and I have to shift now I've got 3 zeros on the top, and I've got to shift it back. It's a big nuisance to do floating point, and that's the complexity there. So floating point is too complicated, and integers don't work. That's the other thing that, well, in order for integers to work, you have to suffer like Paul does in scaling things, and even then it's serious work. And why is that? Well, here are some pictures of histograms of coefficients from, this is ResNet 50. And they all look kind of Gaussian. And the further that you get into the network, the more Gaussian they look and the tighter distributed they are. So unfortunately, they have tails that go way out. So if you want to represent the big numbers on those histograms, The little numbers end up as very right squeezed into the middle of the range plus or minus 128 that an 8-bit int can represent. And so, in fact, a lot of the time when you look at int8 representations of networks, you're really only using 4 or 5 bits most of the time. So half your bits are most of the time not doing anything useful. Now, that's still a lot better than floats because you don't have all the complexity, but it's kind of a shame to pay for 8 bits and only get 4 useful. So you'd like something better, and yeah, we're doing something better, but that's next gen. Right now, int8 is still way, way smarter than FP32. Okay, so you got to avoid moving data. You got to invent new kinds of arithmetic. What have we got next, Paul, on the next slide? Okay, there are a couple other things. So, you know, in university, they teach you that a vector is a long string of numbers. That's actually wrong, because that puts, when I have to do some kind of reduce operation, like when I'm doing softmax and I want to add up all the values, adding up all the values in a long line means your data is traveling a long way. You know, I told you 3D was better than 2D. Well, 2D is still better than 1D. Nobody should actually physically represent a vector as a long line. They should represent it as a square. How should you multiply by 0? That sounds pretty easy to multiply by 0, but it turns out that the right way to multiply by 0 is not even to ask the question. And so you have to figure out the hardware that stops you from even thinking about multiplying by 0. So you've got to do that. 2's complement numbers, that's how we're taught to think about them. But when you get numbers that bounce up and down between small negative, and small positive numbers, almost all of the bits change. That's a bad thing, because changing bits costs effort. So then you look at the TPU. I said it's got a matrix multiplier that really loves a particular size. I think it's 256 by 256 matrices. If you've got a smaller one, it just doesn't use most of the multiplier, and you've paid for the silicon, and you're hauling data past these unused multipliers. And if you've got a bigger one, you've got to cycle several times. So how do you make hardware that scales well? At the front of a network, you tend to have small numbers of channels. At the back of a network, a lot. How are you going to make all that work? You know, when he was out chasing money, Darrick had one of the investors say, "Well, you can't use static RAM. That burns too much power." And the answer is, not when we do it. It doesn't. Our competitors don't know how to use static RAM. We do. Another question, maybe longer term, when you're looking at doing a fetch from dynamic RAM, turns out you're spending about 100 times more power to fetch the data than to haul the data and to throw away bits you didn't actually plan to use than to actually fetch the bit. So how can we not do that? Bigger kind of deep philosophy questions. Should the processing be in Google's data centers, or should it be in your phone, or should it be on someplace in between? And the marketing and the physics guys are saying the answer to that question is yes. It should definitely be in all those places. And oh yeah, so when you look at a network, when you look at ResNet 50, there's no if statements in it. That can't be right. Useful programs all have if statements. So first of all, why did they get lost? And secondly, are you sure you shouldn't have them? Okay, and then there's the ... So here are some of the puzzles we have to solve to get from here to the perfect machine. And as I say, either we do this or they start building coal-fired generating stations again. So it's kind of urgent. Over to Darrick.
Yeah, well, first, if there are any questions, we can answer them, or I'm volunteering Martin to answer them. Or if not, then I'll carry on. People can think of their questions. Yeah, we can definitely ask afterwards in chat as well. Oh, there's a question coming in, I think. So Hong Yu Chen is asking, on the page of distribution, Paul, could you go to that one? Can we just cut the tail part?
Can we just cut the tails? Yeah. if you're willing to do Paul's quantization aware training, you kind of can. The problem is when I cut the tails, I'm making a very large error in a small number of coefficients, right? So you've got something that wants to be 2.3. 1 is the biggest value you've got, so you round it off to 1. So you've made this giant, more than 50% error in the example I gave. So traditionally, when you cut the tail off a Gaussian, you cause massive damage, but to a small number of coefficients. The traditional rule of thumb is 3 sigma. You cut off at about the 3 sigma point, and you hope that you haven't done too much damage. What Paul is saying is, first of all, he looks at some experimental data to figure out where the sigma is, but in practice, it's going to work better if he retrains and suckers those coefficients into range, so you can force it. The other thing, Paul, you might want to talk about how out of distribution works. What happens to your system when you've trained it on a million images and the next image that comes in looks nothing like your stats?
Falls apart, of course. But the next generation models, I don't know.
Well, right.
There's been some pretty interesting recent research out of OpenAI. Their CLIP model, CLIP, can actually, it's sort of pre-trained on just a massive corpus trawled from the web, and it can handle all sorts of interesting distributions. But if you train on ImageNet, so the cats and the dogs and whatnot, there's all these data sets out there that have transformed ImageNet. Now it's like a cartoon of a banana instead of an actual banana, and the whole network just falls apart. So yeah, you need to stick with your data set distributions.
And so in the list of things that need to be invented in the next 6 months or so, if you want to come and invent them, please, is making out of distribution work properly in real time. And I'm talking about the numerics. Well, so the question is, oh crap, somebody just gave me a cartoon of a banana. It turns out that all of my activations now are clipped and making massive errors. So what are we going to do about that?
Just coming back to the original question, this is something that, like, it's a very good question about, clipping basically. And, if you're just looking at the min and the max, then a single outlier can all of a sudden destroy the precision of, the meaty part of the bell there. So we actually have to do some, I was being sort of simplistic when I was talking about using the min and the max. And there's a variety of techniques that you almost have to do like a grid search through, because it varies per network what's going to perform best. But you typically try and find places to clip that kind of, it's a trade-off between the precision of the bell versus how much damage clipping the outliers does. It's a great question.
And question is, but didn't we say we can sacrifice ...
Sacrificing accuracy depends on the customer. That's something that our head of product, he likes to quote that for Facebook recommending ads, if they lose 0.1% accuracy, that's millions of dollars in lost clicks. So it all depends on the customer. It's always a trade-off between speed and accuracy.
Okay.
There's one other question. Is quantum computing viable right now for large-scale computing?
Yeah, not right now. Not at 50 qubits. Although quantum computers are extremely beautiful, and that's important too.
How much power do they use?
I think it depends.
Well, the computing end of it uses microwatts, but it does that by operating at several millikelvin, and the refrigeration to get down there uses kilowatts. So it's very power efficient as long as you don't look at the context. If you're willing to run your quantum computer on the far side of Pluto, it's going to be a lot cheaper.
That's a good idea. Okay, so I'm going to talk a little bit about starting the company. So that's the end of the technical content, unless somebody asks more questions. I'm going to start just by talking a little bit about this picture. So we'll go back a bit. So this is actually one of the nice advantages of working in an interesting startup like this, is that you get to work with very talented and interesting people. So one of our co-op students actually painted this picture. And this is a pretty nice view of our first office. It was Capic's office. I'll talk about a little bit later, and we ended up growing, filling that space as we sort of made our way to our A round. And I'm just going to really talk a little bit about founding and up to the point of the A round, and then stop there. So, okay, go to the next slide. So my name is Darrick. I am another one of the 3 co-founders. Before Untether, I was a co-founder of a pair of conjoined startups, but over the years I've got about 20 years of programming experience, lead engineer on various startups and consulting and various types of all sorts of stuff. One of the things that I really like to do is take on different types of roles, do different types of things, and I really love to build software. So, so what am I doing now is mostly talking to customers and working on our sort of next gen software. Next slide. So before Untether, Martin and Raymond had worked together for a long time, and they had a very high trust relationship. And Martin and I knew each other for a long time. We actually met at Bar Italia, and there's a picture of actually me sitting on a patio of Bar Italia a long time ago. And that's actually on the, I was there so often that it was on the review page of that place. Unfortunately, it's gone, but that was the place that was really the first place in Toronto that you could go with a laptop and sit and work. And I took a huge advantage of that. I lived in the neighborhood, and Martin also lived in the neighborhood, and met each other and became friends eventually. And so, you know, I can't say that, or I can say that one of the things that paid off most of my life is hanging out in cafes. And continues, well, not this year. Anyway, my previous startups were in graph database applications, data center management. And then after my previous startup went down in the flames, I spent a year working with Martin at Capic, and that was great. And it's interesting because it's a really non-linear move for me. It's not a software company. They needed a bit of software, so I joined, and that was great. It was a good decision, hindsight, but a bit of an odd one. I was a bit nervous about it at first, but it worked out great. Anyway, next slide. This isn't all about me. So, so basically, I'm just going to sort of walk through a timeline, and it started out beginning of 2017 when Martin just mentioned to me that he's, now would be a great time to take his ideas from previous research and see if we can make an AI accelerator startup. And sort of gave that some thought. And I had some other ideas that I was thinking about. So it was important for me to really eliminate all of those distractions and decide that this is what I'm really focused on and completely focus on this. And then the next period was a few months, and it was really the gestation period. And for me, that was understanding the ideas, building some models and playing with them. So building very simple software models. And I think I did numerous iterations as my understanding of what we're doing increased, and spent time learning from Martin and understanding his ideas. And the interesting thing is that this was really the only engineering, if you can even call it engineering, before the funding looked safe. And that was also a very conscious decision on my part, because that's the part that I love to do. And I could easily just go down a rabbit hole. But, the nice thing about this startup idea is that it was very obvious that I can't build it myself. the three of us can't just build it ourselves. We're going to need, we're going to need buy-in from VCs, and we're going to need to build a real company. So that was the gestation period of sort of understanding it well enough that I can talk about it, and actually, a lot of what ended up being in our pitch deck is what Martin was just talking about distance and energy, and those are the messages that we were really most focused on in our VC pitch. Next slide. So the next period was the longest and the most painful period, because really there's no noticeable progress happening. Building presentations, talking to people. One of the big questions is, how much money do you ask for? And you have to remember that in the beginning there's nothing. There's some ideas, there's some conversations, and there's some slides of mediocre quality at best, and then you have to basically say that, somebody please give me some millions of dollars, and now we're going to keep the majority of it, so you only get a small piece of what we've got for those millions of dollars. And for me, that's a really hard that's a really hard thing to swallow, just because it's just doesn't feel very natural. The great thing is, though, once I made that decision, and actually I got some fantastic advice. Probably the best piece of advice was from a friend of mine, Guillaume La Liberté, who actually just sold his startup recently. And I met with him, and we were talking about it, and he really encouraged me to ask for more money, because originally we were thinking too little. And if we had raised too little, we would have been dead in the water at the beginning. Another important thing early on is understanding VC terms, right? So, what are their implications, and doing the math on that, and when you're in the conversation with VC, it can, ultimately there was a conversation where it came to a head, and they wanted an immediate answer on the terms, and so we needed to understand that, right? And so it's just an important thing I thought I'd mention. But over this period, we're developing the pitch, testing it, and then that continued right until we got funded. Many versions of the pitch deck, and it's kind of funny, but there were some sort of startup predators that we had to deal with, and these are just people who have their own agenda, and they want to just sort of hone in on something that maybe they think is good, but they you have to be careful, and there's some a lot of accelerators out there are effectively that, I think, and but we avoided those, so we were pretty good. So I have actually a story about traveling to Silicon Valley and meeting our investor, Intel Capital, and basically we had gotten to the point where the pitch was okay. We had done a couple of presentations here, but really thought that valuations at the time, I think it's improving pretty steadily, but at the time valuations were better in the Valley, and so we thought, why not just raise there? And so I went, and there was a conference that I went to, and they have these panel discussions. And so one of the things that I did, and worked out great, was during a panel discussion, I stood up and asked a question, which was basically kind of a little 30-second pitch to about the company, thinking, well, there's probably some VCs here, and maybe somebody will be interested based on that. And yeah, actually, a few people came up to me afterwards. They were curious about what we're doing. As a question, wasn't worth much, but it did serve its purpose. And that actually, that is how I learned about another event that was, the first ever event held by some group that was semiconductors and VC. And so like, okay, great, that's perfect. So I went to that. That was a couple of days later, and and at that event, I basically did the same trick. But that time it was a smaller group, and I was able to be a bit more strategic. And I sat beside the guy, or the couple of guys who looked like they were the most serious investors there. And those actually were the guys from Intel Capital. And so I stood up, did my same kind of spiel, and I just got the tug on the arm from the guy who turned out to be our investor, and said, "Hey, okay, stop asking this stupid question. Let's go talk about it." And we talked. We just kind of walked out of the presentation and talked about it. And next day, I went to the ICAP headquarters, or ICAP's offices, and sort of went through in more detail. And that started off a fairly long process as well, where they were evaluating us. And but it was interesting because that was a trip that I went. I had one agenda item, which was on the first day, going to this short conference, and then I stretched it out for a couple of weeks, just thinking, okay, I don't have contacts, but I can work. I'll work the Silicon Valley, and like, it's really a monoculture. So there's you can really talk to people, and one or two steps down the social network, and you're at important VCs. So I got VC meetings that with good VCs, where later on, when we were doing our A round, our investors recommended those VCs. I had already met them through my networking, and it was only a couple of weeks there. So that was a pretty focused networking set. Okay, next slide. So, time passed. On Valentine's Day of 2018, we got funded, and then from then, really from the moment that we knew that we had a strong confidence that we were going to be funded, the real engineering effort started. And so that was putting together the core team, just a handful of people. It was very small, but that was where the contacts that Martin and Raymond had really paid off, because there's a lot of specialized talent required in the making of computer chips. So their years in the industry was absolutely invaluable, and others, people at Capic, David Lynch and many others were very helpful. And it was great to have those resources and be able to use these preformed teams and these people who knew each other through this fairly tight Toronto network, and get that first chip built. And that was, when we delivered a working silicon, our investors were really impressed, actually. And that was them seeing that we were able to do that we were able to do it on a really tight budget with just seed funding, was, what really drove us with a large amount of momentum into our Series A, right? And so there were some pieces where we had to, there's a lot of verification that goes into building a chip and making it work. And one of the places that I think we really excelled was in automating that. So of course, we excelled in a lot of places. And watching the budget was really critical as well. I think there was a point about halfway through where we realized that we were on a trajectory where we would run out of money if we didn't adjust. But because we were on it, I don't think we were on that trajectory for more than a few weeks. So, so we were able to adjust. And when we raised our money, when we raised our Series A, there was very little money left, but that worked. And that's really what you want. You want to maximize your use of your resources in a startup, and you're basically going full tilt towards fairly dangerous and scary looking obstacles, and you have to kind of trust that you're going to get the things that need to be done in time, right? And so but it's a lot of fun, right? So hard work but fun. And I think that's the end of my slides. Yeah. So questions. I see there's a few questions in here. A question if we make ASIC chips. Yes, we do.
You guys mind if I just ask a question this way?
Yeah, of course.
Okay. So I'm curious about, like, do you guys work? So I've been personally reading a lot into memory-assisted technology recently. And it's like an area which I'm doing some research in. Is that something that you guys are working with? And if so, like, and if not, like, why not? Like,
I didn't quite understand the question.
Oh. So I'm personally quite interested in memristor. So just like memristors, and they seem really promising for like in-memory computation. So is that something that you guys are working with, and if not, what is your platform based off of?
No, we're not actually. So So one of the important things about our architecture is that there's nothing in it that requires advances in the state of the art of ASIC chip making itself, right? Our chip is a vanilla process, which is great because that means that you can scale along with the process scaling, right? So as companies like TSMC, Intel, Samsung, SMIC, and any of them come up with more and more advanced semiconductor manufacturing processes, then the only barrier to us adopting those is the cost. Right? There isn't a technical hurdle, right? So if you look at some of our competitors doing in-memory or other complex, other more R&D type of work, they are locked on a specific process that they develop. So one of them, I can't remember their name, is stuck on 40 nanometer. And 40 nanometer is old. At this point, you're really out of luck if you're on 40 nanometer. Where we can scale with the,
okay, yeah, that's not something I thought about. Yeah. Thank you.
Yeah. Hongyu.
Hi. Yeah, thank you for the presentation. It's very inspiring. I have a question about, so like I can see there are already like tons of companies that's doing AI chip right now. And I'm wondering, when you started this company, what makes you think that you guys have a unique strength that you can compete with them?
I think uniqueness wasn't too concerning because it's a huge space for design. And also I think that, the idea really comes from Martin. And Martin's unusual in that he's got a a lot of experience both in the analog design side and in the digital design side. And it's quite rare in the industry. So to be able to combine the insights from both of those in order to create a digital architecture which takes into account the analog nature of circuits and deeply understand the energy trade-offs and stuff. We knew that there aren't many people who really can think about the problem in that way. And so, but then the other thing is that if you execute quickly and well, then even if there are others with the same idea, you have at least, you have at least a good chance of winning that competition.
I see. Okay, thank you.
Yeah. So there's a question if we specialize in making ASIC chips. Yeah, I guess the answer is yes, that our product is an ASIC chip, and together with the software that goes with it. And the type of work that Paul does, which is not directly in the chip, but it's critical to making the chip work and to how we design the chip. And the other question is, do we design the software, create the software? And the answer is yeah, we do.
I got a question.
Sure.
So it's interesting. So when I'm a second-year student in ECE at U of T, and I was kind of having this idea that Untether AI, the presentation was going to be mostly just about like the programming side of things. But it's interesting to see all the different levels, like, the fact that it's machine learning, programming, there's that aspect, but there's also the huge aspect of hardware and analog and digital design. And so I was kind of wondering, when you guys are looking for talent, for people to scout, are you looking for people who are highly specialized in one thing, or are you looking for, people who are kind of like Martin, as you were describing, someone who can kind of dip into multiple aspects of the project and give good feedback or, good input?
Yeah, I think that the experience that I've had is that the company requires primarily specialists and a handful of generalists. Really helps to integrate it and to make sure that ideas in one group are understood by another. And but specialists are absolutely critical for being at the state of the art in every area that we're in. And so if a generalist can also be at the state of the art, then that's wonderful, and that's something that Martin, so Martin is, I guess you could say, a sort of generalist, but at state of the art level in multiple areas. And then, of course, that's fantastic.
It's a rare find.
Yeah.
Thanks.
A question is, how fast are we growing? We grow, I would say, in fits and starts. So we had a very rapid phase of growth about a year ago. And then we basically got to the level that we wanted to be at and then stopped. And now we are starting to grow again. So how fast we will grow? Potentially very fast. If it's a startup, so things have to go well. If they do, we will grow very fast. Anything else? Okay, well, it looks like Martin had to leave already, and I think we're done.
Yeah. Are there any more last? Yeah, for sure.
Yeah, just out of curiosity, so like for the quantization part, what are some of the real life applications? Right now we have actually have a relatively higher tolerance of accuracy loss, and usually we use a quantized model to do that.
Sorry, are you saying what are the applications if we have a higher tolerance for accuracy loss?
Yeah.
Oh yeah, so I mean quantization, there's some really interesting research that goes down to, even a single bit. So you can quantize down to a single bit if you're okay with the accuracy repercussions. And so, given specialized hardware, you can start to run things extremely fast, and you can take really big models and compress them down to very small sizes. And so you can run potentially very powerful models on the edge in IoT devices and that sort of thing. So quantization has a huge applications in IoT devices, which are very resource limited, and there's a lot of research into really being able to quantize very aggressively to be able to fit onto these devices. And yeah, so that's where if you have a tolerance for accuracy degradation, that's where you would be looking is to quantize really, really small and put them in IoT devices and another resource constrained devices.
Yeah. I guess the question is what kind of application usually, what tolerance those accuracy loss then?
Oh, yeah. So like object detection is I mean, not in a self-driving car, you really don't want to have significant accuracy degradation there. But if it's sort of detecting pedestrians or something like that, something that's not mission critical. Basically, I can answer the question the opposite way. So the things that are mission critical are self-driving cars, healthcare applications, space applications. These are the things where, and also recommendation systems where there's a lot of sort of money on the line. These are the things where accuracy is significantly is very, very important because you can't really afford to make mistakes. And so other applications where you're more just fault tolerant. So maybe it's just counting pedestrians. Maybe it's much more simple kind of applications. That's where you would see these sorts of things.
I see. Okay, thank you.
Okay, if there aren't any more questions, then I think it's time to wrap up tonight's talk. Thank you everyone for listening tonight, and thank you Paul, Martin, who's currently not here right now, and Darrick for sharing us Untether AI's development and story. It was great to hear also technical understanding to complement what we're learning in school. I think definitely the students here are going to carry forward something. Yeah, if anyone is interested in contacting Untether AI or UTMS, we did share a slide that has links to it, and also you can see the screen shared, which has Untether AI's contacts. And that's all. So thank you everyone for joining tonight.
Thank you for having us.
Yeah, thanks. It was fun. Bye.